YouTube. Okay, so I think we are all set by now, and also switching to English for a wider audience. So thank you all for joining. It's for me really a great pleasure to introduce Alexandra Silva, who is not only, say, a great researcher, clearly, but also a dear friend. So I will take literally a couple of minutes to introduce Alexandra. I'm sure that there's way more to say about Alexandra, but I try to be really synthetic and leave most of the floor for her, of course. So Alexandra has just joined Cornell University as a professor at the Department of Computer Science, which is part of the newly formed Bowers College of Computing and Information Science. And until recently, she was a professor of algebra, semantics, and computation at University College London. Prior to that, she was an assistant professor in Nijmegen and a postdoc at Cornell with Dexter Kozen. And even before that, a PhD student at the Dutch National Research Center for Mathematics and Computer Science, so CWI, under the supervision of Jan Rutten and Marcelo Bonsangue. Alexandra's work has been recognized with numerous awards and distinctions. She was the recipient of a consolidator grant by the European Research Council in 2020. She received the Royal Society Wolfson Award in 2019, the Needham Award in 2018, the Pressburger Award in 2017, the Leverhulme Prize in 2016, and she also received a starting grant from the European Research Council in 2015. So Alexandra does research on programming language semantics and verification broadly, and she's interested in developing new algorithms for verification using automata, and in particular for network verification. A lot of her work uses the unifying perspective offered by coalgebra, which is a mathematical framework well established, especially in the last decades. And in her keynote today, Alexandra will present Prognosis, a framework offering automated black box learning and analysis of models of network protocol implementations. So I would again like to sincerely thank Alexandra for accepting our invitation to deliver this keynote at the Brazilian Symposium of Programming Languages. It's really a great pleasure. We are looking forward for your talk. So the floor is yours, and thanks again for joining us today.
Thanks, João, for the kind and long introduction. It's one of the more detailed introductions I've ever gotten. As you said, I was a PhD student at CWI, but before that, I was actually an undergraduate student at University of Minho in Braga in Portugal, where João and I met back over 20 years ago now. And João is a dear friend and has given me the best role ever that trumps all the prizes and professorships, which is I'm the godmother of his eldest daughter. So that's my favorite job, is being the godmother to two beautiful girls. So, but today, I'm afraid that I'm going to bore you with work, and I'm going to talk about a recent project I had with a couple of colleagues at the University of Wisconsin-Madison and one of my undergraduate students at UCL. So as João said, I just joined Cornell. When I did this project, I was actually on sabbatical at the University of Wisconsin-Madison last year, and we were working together with my undergrad student, Tiago Ferreira, who's also Portuguese and living in London. So this work appeared about a month ago at CCOM, conference on networking. And I would like to tell you not only about the tool and what we did for the tool, but a little bit about the broader context of the work, and also how this work came about and what is underlying it. So João said in his introduction that I broadly do research in semantics and verification. And if I put on my hat of semanticist, a lot of the times the questions I'm trying to answer are of the sort, what does this program do for a certain program in a certain language? The verification hat asks a slightly different question, which is, does this program satisfy a certain number of requirements? So the program might not be doing exactly what I want it to do, but as long as it doesn't break the requirements, I'm quite happy. And these two questions are many times taken very differently, and there are very different approaches to answer each of these questions. But in fact, what I want to argue is that these two questions are very connected, and they are really the two sides of the same coin. So more concretely, when you're asking what a program does, a lot of the times you have this program written in a high-level language. Perhaps it's a programming language or it's still a specification language, but you have some high-level language in which you have written this program that might be capturing a certain algorithm on a certain data structure, and you want to sort of understand what is this program doing. And so the way a semanticist will go about it is to say, okay, we need to first understand what are the behaviors that any program can have in this language. And so one tries to define a semantic space, which I call sigma here in the slide, into which we can map any program in that language. On the other side, in the verification side, typically there's a list of system requirements, and these might be written in English. You might have a protocol that is described in English, and you want to ensure that a certain implementation of that protocol satisfies those requirements. So very often what happens is the English description is translated to some formal language. So perhaps some logic, which I denote here in the slide by psi. Now, ideally, once you have the program and you have the requirements and you have everything sort of formalized in a very concrete mathematical object, ideally what you would like to do is to basically take your program, take your description of requirements, and you would like to basically combine those two descriptions and be able to say, this program is correct, or this program is bug-free, or any sort of approximation of these questions. Now, in practice, this is not quite so easy because these objects, sigma and psi, are typically very far away from each other. So, as one example, you can think of sigma is very often a set of traces. So you have your program, you have your control flow graph, you have your data flow graph, and then you look at the traces of everything you can observe in that program. The system requirements can be formalized in very different ways, but one way could be to have a temporal logic formula telling you how to formalize a safety property, etc. Now, these two things live in completely different worlds. So mathematically, they are not the same thing. So if you want to answer the question, does this set of traces that denotes the behavior of my program satisfy the requirements that this formula specifies, you need something to help you connect these two worlds. And that connection, that bridge between semantics and verification has been understood for many decades now, and is provided through automata. So finite automata, not necessarily deterministic, but with different features, provide this neat bridge between many spaces of semantics, like sets of traces, and many logics, for instance, temporal logic. And so what typically happens is you have a program, you have a certain semantic space, you do the translation, you then take your set of traces and you convert that into an automata representation. And usually you have some temporal formula or a set of formulas, and you can convert each of them also to an automata representation. And then at that point, you have two automata representations. So you're suddenly living in the same world, and you can combine them and answer interesting questions about the properties of the system and how they connect to your temporal formulas. Now, automata are also important because they are really good data structures and they are very good for implementation. So they actually, automata form the basis of many, many tools. One sort of technique or tool that automata play a key role in is model checking. So the idea behind model checking is that you have a model of some system component, could be a little piece of hardware, a little piece of software, or just a protocol that is running. And you have this model as an automaton. The automaton might be very large, might have many transitions, might have a very complex alphabet, but you have this model. And you have certain properties that you wanna, that are your properties of interest, and you wanna sort of verify to be able to assert that the system requirements are true. And so what a model checker does is basically taking this automaton representation of your protocol and taking your system requirements that are formalized in a logic, and it will basically give you one of two things. It will either say that your property of interest is valid and give you back a green stamp, or it will tell you that actually the property you're interested in is invalid. And then what is interesting about model checkers is that typically they give you back a trace on why the property is not working. So like in this case, there's huge protocol here on the slide, and there's a red transition there that the model checker would return to alert you that that transition should not be there. And that's why the verification failed. Okay, so this procedure that model checking proposes has been very successful. The inventors of model checking were recognized with a Turing Award back a few years ago, I think in 2007 or 2008. It is one of the most successful formal verification techniques. It has been adopted inside hardware companies. Intel and ARM use it in their daily engineering production, and it is extremely successful. However, there is a very niche application in which it is used. And one of the reasons for that is that for more complex software components or protocols, designing a good model is not easy. So there's always the question, how do we design a good model? And then more worryingly, how do we maintain it? So you might have a model in the beginning of the production of a project. You use the model, you do all kinds of verification on this model. You're super happy. You say, great, version 1 of our software satisfies all these requirements. The week after, the client wants a new feature, and someone goes in, replaces a little component to provide this feature, and suddenly forgot to update the model. So you continue using that model, you continue saying system requirements are all fine, and then there's a security breach. And then you don't know how that happened. Well, it happened because when the feature was updated, someone forgot to update the model. So in fact, the model was completely out of date in comparison to what was running. And this is sort of one of the drawbacks of model checking, is that one assumes that these models exist, are there, and magically get updated. But in real projects, that doesn't happen. So already the assumption that someone will take the time to produce a model is already a very unrealistic assumption in most contexts. So this is a very heavy thing on the teams. And as we know, resources are limited and people will only do it if it's really worth it. And in many cases, people don't recognize that doing model checking is worth. For companies like Intel and ARM that produce hardware chips, it's a bit different, because if there's an error that can be found before production, the amount of money they will save by not producing a range of hardware chips is very high. For a software company that can release patches every other month or even every week, it doesn't really matter if there are some mistakes found along the way. Unless those mistakes cause great financial loss or life loss, people will be less likely to use heavy formal methods in real production lines. And that is a bit of a shame. And many researchers have sort of tried to get around this drawback of model checking. And one technique that has sort of emerged in the last 5-10 years is something called model learning. So the idea behind model learning is that, okay, you need a model of some running protocol, and you didn't take the time to build the model when you implemented it, you just implemented it. But now you would like to have it because it would be convenient to basically get some assurance that the properties of the model are correct. The properties of the code are correct. And so model learning basically provides a way to taking a running piece of code, building a model automatically. And so the way it works is that you have your system requirements that will guide the building of the model, and you can interact with the code black box. You don't even need to have access to the actual source code, but you can interact with the code in a certain fixed way. And by interacting with it long enough, you sort of learn the patterns in your code. And this is sort of, you don't learn a model of the full code, but you learn a sort of view of a part of what's going on in the code. And that is the part that is relevant to verify certain requirements. So for instance, the example I will give later on, if you have a protocol that has a handshake part and then a bunch of other things, and you just care about the handshake happening before any communication occurs, then you can basically focus your model learning algorithm to learn just the handshake part and ignore all the rest. And so then you can sort of analyze a small fraction of running code. So model learning does not provide, it's not a free lunch. It does not give you for free a model of the whole code, but that's fine because no one expected that to even be possible given the complexity of many software projects. But what it gives you is an automated way to learn fragments of the code. And those fragments, it's all up to the user to say which fragments are important. And by focusing the learning process, you will basically distill automatically a bunch of models that can be used for verification. And as I said, the properties of interest that you have for your model will guide this process. So it will make sure that you can build the model effectively, but also that every time you need to update it, you will make sure that you have enough information to actually say something about your properties of interest. And what makes model learning a popular technique, and it's becoming more and more popular in industry, is that it's a fully automated process. So you can leave it during the night and you come in the morning and there's an updated model and you can run your verification tools and check whether the properties are still holding. So that's a big plus in comparison to the usual manual building of models that a lot of model checking has relied on. So now I would like to make this very concrete just to so that you can see what a learning algorithm looks like. And in order to make it concrete, I'm actually gonna show you an algorithm that goes back to the 80s by Dana Anglin. And this works as follows. I mean, you have a teacher that holds in a black box some language, and we're gonna assume this language is regular, meaning if a language is regular, it can be represented as a finite automata. So this teacher is sort of holding on to this language L, and it knows that it's regular. And you are the learner, and you're trying to figure out which language the teacher has hidden in his black box. And so how do you do this, and how does the algorithm work in order to build the minimal DFA accepting L? So you can do two things with the teacher. You can ask the teacher, is a certain word in the language you're holding, and the teacher will answer yes or no. So let's imagine that you ask, is the empty word there? The teacher says yes. Is A there? The teacher says yes. Is B there? The teacher says no. is AA there? The teacher says yes, and at that point you say, ooh, I think I know what it is. It's the language of all words with just A's. And so at that point, if you make a guess just by asking the teacher questions, you actually can do a different type of query, which is called an equivalence query. And in an equivalence query, you give the teacher your hypothesis. You say, here's my guess of what the language is. And you give this guess usually in terms of an automaton. You say, here's the automaton that accepts that language. And at that point, the teacher will either say, yes, your guess is great, or it will say no, and it will give you a counterexample. So maybe the teacher says, actually, you're wrong, and the word AB is also in your language. And so at that point, you can use the counterexample to refine the knowledge you have on that language, and you can do more to basically build a new automaton. And so at the core of this algorithm is this data structure called an observation table, which is just a matrix in which you start storing everything you ask the teacher. So every time you ask a membership query, you add into your table the results. So like A was not there, AA was there, B was not there, AB was not there, etc. And the nice thing about observation tables is that they are a faithful representation of automata. So in fact, there's a one-to-one correspondence between deterministic finite automata and observation tables. And this construction is very trivial, and you can move from one to the other very easily. And so as you're building your observation table, you're actually at the same time building several hypotheses for what an automaton might be for the language. And every time you do an equivalence query, you provide your hypothesis automaton to the teacher, and the teacher might return a counterexample that you will use to refine that hypothesis and to basically expand the table. So for instance, this red column in this table is the result of a counterexample that basically told me my table is not correct. And with that counterexample, I managed to expand it in one dimension. So you might wonder, this algorithm, I mean, it builds a deterministic finite automaton, and deterministic finite automata are, one could say boring because they only accept regular languages. So you might wonder why I'm showing you this algorithm. Isn't this too trivial? Moreover, I'm assuming the teacher is a perfect teacher. So I'm assuming that, this teacher basically knows everything. And in real life, you don't have a perfect teacher. So how do you do that? And so you might wonder, does this work at all in practice? Now, surprisingly, L star is very powerful, and you can do a lot of verification work with it. So let me tell you a little bit about the things that people have done in the last sort of 5 years, just using L star for deterministic automata. Here's one, and if you look carefully at that automaton, you might recognize this is the example I was using before. This is a model of Windows 8 TCP implementation. And basically what Paul and this Ramon and Fritz Vandracher did was look at several implementations of TCP and use model learning, guided model learning, to derive different models. And in the model of Windows 8, they actually found the bug, and they reported that bug, and that bug has been fixed. What else can you do? Well, here's another example. You can take programs. These are error traces of Java programs. So you can take Java programs, and using a combination with bounded model checker, you can basically derive automata that capture all error traces. Then another one, again from a group in the Netherlands, is they learned a formal model of a bank card, namely MasterCard. And this one is the model of the Visa debit. But in the paper, they have a MasterCard and they have other things. And in some of them, they have actually found flaws in the protocol, not serious flaws, but sort of underspecified things that made the protocol a little unsafe. What is interesting about the bank cards, and also there's another example of a passport, is that you can actually, the protocols are so small that you can actually learn the full model. So the third example here on the slide, this is the full model of the authentication protocol that runs inside Visa Debit. So this is not a fragment. Whereas in the other two examples, both in the Windows 8 TCP and in the function calls, these are fragments of programs that are inside a larger piece of software, okay? So already with deterministic automata and regular languages, you can do a lot. Now, is this enough? No, it is not enough. Especially in today's landscape, we have lots of other models that we would like to use for verification. We have models that talk about congestion, we have models that talk about data, we have models that talk about concurrency. So, you know, L star for deterministic automata is nice and has some applications, but it's not enough. And the original algorithm was done in a way that correctness was quite trivial because it was deterministic automata, but ultimately we would like to have algorithms for different models that all sort of share the same sort of correctness proof and the same sort of termination analysis, and that we can use optimizations. And so in the last sort of 3-4 years, I've been working really hard with some students on developing L star-like algorithms for more expressive types of automata. And all of this has been done using category theory as the correctness technique, and that's allowed us to actually expand these algorithms much beyond what Anguin had done. And we have applied them to different verification contexts. Now, these sort of more general models become really hard to use in practice, I must say. And so this as an algorithm design project was really nice, but when it came to actually apply it in a practical context, things were a little bit harder. And so this is now, I want to sort of switch gears and show you how we build this tool and exactly what models we picked and how we have used them. So let's take a pause here because now we're sort of switching gears a bit. So I've told you about model checking and model learning and sort of the general context. And now what I want to show you is a very specific application that we've chosen to apply model learning and model checking. So we wanted to look at network protocols. And we wanted to do this, so we wanted to build a tool that would be good for what we wanted to do, which was network protocols, but that it was general enough that one could replace modules and use it in different areas. So here's the sort of architecture of our tool. We assume that the tool is going to be used by a human that will provide us with a couple of things. So the user will give us a property set, so a list of requirements, and also an alphabet. And I will say in a moment what this alphabet is. Once that is there, we have built into the tool both a learning module that comes with a bunch of learning algorithms, active learning algorithms like L star and optimizations. And we have also built an analysis module that has built in some model checking techniques, some other things that can be used. At the top is the system under learning. So this is the code we're trying to analyze, or the protocol we're trying to analyze. And both the learning model and the analysis module will have to interact with this system. And this system can be black box. We don't need to have the system being open source or anything like that. Well, inside this system under learning, there's the implementation, which can be black box, but there's something else, which is very specific to the architecture of this tool. Inside the system under learning, there's going to be this thing called an adapter. And the adapter will have a reference implementation, and it will have these translation pairs. What are these translation pairs? So the user, let's imagine that we're looking at the TCP example that I showed a couple of slides ago. We have concrete TCP packets that can be used to interact. And we have the learning algorithm. Now, these TCP packets, if we use the real TCP packets, there's just too many of them. And so when the algorithm starts doing membership queries, it will hang because there's too many queries to be made. So what we do, we say, okay, we actually, for learning that particular, for instance, fragment of TCP, we don't need to use all of the TCP packets. We just need to use some very specific ones. So in fact, we just need to know something about the way let's say the handshake works. And so what the user will do is tell us what part of the algorithm or the protocol they want to learn through this abstract alphabet. And then the adapter will basically have a way of building from the implementation concrete TCP packets and then translating them to abstract symbols for the learning algorithm. So what the adapter is doing is basically translating between what the implementation actually knows and what the learning algorithm can recognize. And this adapter is usually a lot of work. So what the previous work had done was build this adapter by hand. So build all of the sort of TCP logic into the adapter, which is in essence a little bit counterintuitive because it's almost as hard as building a model. So what we did, and really the novelty in this work, is to say, well, for things like TCP and other network protocols, we have tons of implementations around. So what we're going to do, we're going to take a reference implementation, which might or might not be correct, as a sort of driver for our adapter. So the reference implementation is going to teach me how I translate from concrete packets to abstract packets. And we're going to use that, we're going to annotate that and use that in the learning process. And so what happens in the end here in this thing is that, let's imagine the implementation is, so this is a fragment of TCP. It's the handshake part. So imagine we have an implementation of this protocol, which I depict here just without the code. Then the concrete symbols, as I said, are going to be TCP packets, and they are going to look a bit like this. They have, more than 10 fields, and they have all kinds of numbers associated with them and all kinds of information. But in fact, for the abstract symbols, we don't really need to have that. We actually are happy enough with just checking if a certain packet is an ACK packet or a SYN packet. And so all the information in the TCP packet is a bit overkill for what we want to learn, if we just want to learn that fragment of the code. And so for this particular example, once you have that, you can actually learn this little three-state automaton. So you can learn this in an automatic way. You can learn this three-state automaton, and you can see that the three-state automaton very closely captures what the client-server communication is doing. And once you have this automaton, you can also see here that there's some interrogation marks in the alphabet. And basically what we did was to say, okay, a lot of the alphabet symbols in these protocols, they have parameters. And the learning process is not smart enough to learn the parameters as well. But what we can do, once we have the template of the model, is synthesize those parameters by observing the traces. And so the automaton on the far right is actually automatically produced from the automaton on the left by looking at the traces and inferring the connection between the parameters. So in this case, basically the only connection it infers is that the parameter R, after you do ACK and SYN, it has to be SN plus 1, where SN is the first parameter. So it's basically the number in the first SYN message. And so this can be basically all done automatically. And that particular three-state automaton is actually a fragment from that very large Windows 8 model I showed you, and it recovers faithfully that three-state fragment. And in order to recover the rest, which has another 10 states, what we would have to do is basically extend the alphabet to give the tool Prognosis permission to basically explore further in the code. Whereas with the alphabet we gave it, which was just with sin and ac, the only thing the tool could do was basically exploit these three states. So TCP is sort of simple, and by running the learning process longer and longer, we can actually learn an almost complete model. But as I said, when we designed Prognosis, our main goal was that the tool would be flexible enough that it could be applied to other things and to more complex protocols. And another thing we wanted to test is the theory that once you have these models, they actually can be very helpful to developers. So developers can actually use them in some effective way. Now, if you see the full model of TCP, it looks a little bit like a spaghetti diagram. And then you might wonder, is this really effective for developers? I mean, a human looks at it and cannot say much. A tool can happily verify whether certain properties are true. But what can we give the human in the loop? What can we give the human as information that will be useful in finding bugs? That's sort of another question. So what we did once we sort of had run this proof of concept with TCP and recovered the results that previous researchers had also done, we looked at this new protocol called QUIC. So QUIC is a new protocol that is going to basically in the coming few years is going to be replacing TCP in the communication layer. And if you look at the sort of handshake process of QUIC, you will see that it is much more complex than TCP, in particular because it has TCP inside and then it does other things. And so what happens is that QUIC will basically replace part of those layers, and it sort of takes a little bit from each of these layers. So it takes a little bit from TCP, it takes a little bit from TLS, it takes a little bit from HTTP, and it sort of compacts it into one very complex protocol. And so we wanted to sort of test the tool in QUIC for two reasons. One, QUIC is more complex, so we were sort of curious whether the tool could cope with that. But two, QUIC is very recent, and there's a bunch of implementations, but no one quite knows how the design choices were made. Whereas for TCP, TCP has existed for many decades. There's been a lot of projects verifying implementation of TCP. The developers have gotten really good at knowing where the bugs might be in a new implementation. Whereas QUIC is a new protocol, it has just recently been standardized. It's a little bit more of a good playground for formal verification to help out. So this is the sort of handshake of QUIC, how it looks like sort of when it is encapsulated. And this is the sort of fragment of the code that we're going to focus on. And just a comment that QUIC packets are much more complex than TCP packets and have all sorts of crypto information that makes the packet itself a much harder thing to abstract. So we, in fact, have abstracted this packet into an alphabet with only 2 letters, which you might wonder how far we get with this. But basically what we did was to say, okay, we only want to learn the diagram that you see here on the slide on the right. And in order to do that, we only really need 2 things. We need a way to initiate the communication, and that will come with a crypto frame that is needed to establish communication. And then we need a way to receive back the acknowledgement and the stream frame that, that the server sends back. And so with these 2 things, we're going to sort of hit a few implementations of QUIC. So what have we hit? So for TCP, we had looked at an Ubuntu TCP implementation. And as I said, we've recovered a model. And just to give you an idea of the members, sort of the number of queries we had on this, there were about 4,700 membership queries. And the results on TCP replicated the previous results, but we only had about 300 lines of extra code to do that, whereas the original paper that implemented the adapter from scratch had about 3,000 lines. Now, for Quick, we decided to look at 4 implementations. We took Cloudflare's implementations, implementation called Quiche. We took an implementation from Google and one from Facebook, and then a reference implementation called Quick Tracker. We run the tool on it with that 2-letter alphabet. And what happened was that it took about 10,000 and sometimes even up to 25,000 membership queries to learn an automaton. And this really shows the striking difference between TCP and Quick. I mean, we're learning the sort of same fragment, just the handshake part, and it takes us about 5 times the number of queries. The model sizes between these implementations varied quite a lot. So some implementations gave rise to a model with 8 states, some with 12, and then the transitions were something between 50 and 80. As we did this, because we had these 4 implementations, and they come from these large companies with very good programmers, etc., the first thing we did when we got the models was to run an equivalence check on them. And we wanted to know, are these models doing the same thing? And as we did that, we actually discovered 3 bugs in some of these implementations, which I won't name specifically, because some of the bugs were induced security flaws. I think in the meantime they have been fixed, but we found bugs that were there because there seemed to be some confusion with one part of the protocol. And we talked with the developers, and we talked with the IETF, which is the body that basically regulates the Quick specification. And in the end, we filed an RFC change. So they changed the way they described that part of the protocol because they realized that actually it had been left so unspecified that developers could write code that was completely not the intent. And so for Quick, we had to do about 2,000 lines of annotations in our reference implementation. So again, if you compare it with the 300 lines of TCP, you see that the complexity is really in the next level, if you like. So I'm almost done. I'm aware that I'm almost running over time, but just to give you a sort of quick idea on the type of bugs, these 2 I can sort of safely show. So in the Facebook's implementation, while we were learning, we noticed that there was this sequence of actions that sometimes returned an action that said that the frame was going to be closed, the connection was going to be closed, and sometimes it just didn't return anything. And as we did this more and more to sort of see if there was a problem in our implementation or what it was, we realized that actually the implementation was non-deterministic. And at that point, what was really cool was that from our model, we could generate these concrete Quick packets. So from this sort of 3 sequence of abstract letters, we could generate these very concrete Quick packet traces, and we could send them to the developers and ask, did you expect to see this? And the fact that we could generate those concrete packets meant that the developers could go back to their own implementation and could run tests on it, and then would come back and say, actually, no, that's a bug and we need to fix that. Or, sometimes they said, no, that's fine, that's the intention. And this is one thing that is really nice about the tool, is that it gives you this way of generating tests that then the human in the loop can use. In the case of the Google's implementation, we learned the model seemed fine, and then we tried to synthesize the parameters for the Quick, for the letters, so the interrogation marks in the alphabet, we tried to fill them in. And we realized that one of the values, one of the parameters had been set to be a constant. So the parameter that basically had the stream ID was set to be a constant, whereas in the description of the protocol, it clearly says that this is a variable length integer that shouldn't be a constant, basically. And so we went back to the developers and we said, look, in our model, it seems like this parameter is a constant. Is that intended? And they realized that from the original implementation, they had sort of forgotten to replace that. And so that's sort of a nice application of this parameter synthesis and how you can then provide feedback based on that. Okay, I'm sort of wrapping up. I hope I gave you a sort of glimpse on how certain classical programming language semantics and verification techniques like model learning, model checking, equivalence checking of models, etc., can be used to analyze network protocols, both the design and more importantly, the implementations. The fact that we had Quick to sort of attack was a sort of nice timing, because Quick, being a new and complex protocol, is a really nice playground for this sort of techniques. And our hope is that the tool is modular enough that it will easily be adapted to other protocols. And we're hoping that it will be used to also analyze protocols that are not network protocols. And with this, I'm happy to take some questions.
So thank you very much, Alexandra. Thank you. It was really nice. Yes, I would open the floor for questions. Does anyone have any questions? Not really sure whether people can unmute themselves, but I hope so.
Should I stop sharing my screen, or?
I think you can keep it on. I don't think it's a problem.
Okay.
Maybe I can start with a couple of questions. I have a few, and well, people will follow surely. So I have so the first two questions that came to my mind during your presentation are sort of related. So my first question was whether you could motivate a bit more the choice of network protocols to well, as a study object. And related to this, and I think that this also comes back to your previous slide. So how do you, well, so what are the characteristics that, say, network protocols have that allow you to say or to say transfer what you have done to other domains, and what characteristics of other domains make it, say, more challenging to do that?
Yeah.
Can you?
Yeah, that's a great question. I mean, so the reason why we chose network protocols was, well, I suppose twofold. One, because other people have tried similar techniques and it had worked. So we were like, okay, this seems to be a good point. But to be a bit more specific, I mean, the reason why other people have tried as well is that network protocols, in their description and in a lot of the RFCs, they already have a sort of finite state automaton flavor. So there's the description of these protocols already look like automata. So the chance that an automaton tool is going to be able to recover that description was high. The other reason, which is really important for our tool, not so much for the previous work, but for our tool it is really important, is that protocols like TCP and even now Quick have been implemented many times. So there's like many implementations of the same thing. And that makes our work much easier, because if you have several implementations, what you can do, even if you don't trust any of them, you can pick one to be your guide, and you can learn the other ones. And then you can switch them around and do the same thing. And in that process, what you get is always more information, because you have different models of the same thing, and you start collecting more and more information. And so that's what makes network protocols such a good playground for these techniques. In terms of other domains, I should have been a bit more specific. I don't believe that this technique will be helpful in very generic sort of, let's say, software development. I think it will always depend on the fact that we need access to different implementations. And again, bank cards or protocols running in bank cards, in passports, in anything that has a sort of authentication protocol will be a good playground, because again, you can sort of hope that in finite time, you will be able to cover enough of the space that you can learn something interesting. Things in which a lot of data is involved then will be less interesting or less, say, applicable in this work.
Yeah, I see. Thank you very much for the answer. So, any further questions? I have more, but I really don't want to take over Q&A. So can anyone just confirm that they can unmute themselves? So I'm just, yeah, go ahead, Karina,
yes,
please.
We can.
Thank you.
Yes.
Okay, perfect.
Thank you for the talk. I had to say that I am a person that loves topics about model checking, about automata, and so on and so forth. But I'm always afraid of networks and protocols and this kind of stuff. And I don't remember when I thought, wow, it's something about networks and this is interesting. So I'm very happy with that. So thank you very much. I think it's a trauma that it's being done now.
Yeah, thanks, Karina.
Yeah, that's right. And you talk. I remember in the beginning that you talk about category theory, and I don't know if you have something that you apply there about with category theory with this developing or it's just two things that it's part.
Yeah, so category theory was used here, well, not in this particular development of Prognosis, but category theory was actually used to design generalizations of this algorithm. So there's some part of this work on the side where you can use category theory for generalizations and to have better proofs of correctness.
Nice.
Thank you, Karina. Thank you, Alexandra. So, Roberto, you have turned your camera on. Does that mean you want to ask a question? I guess so.
No, sorry.
Oh, no problem.
Just to show that I'm
participating.
You asked if we could answer.
Yeah,
but sorry, I don't have questions.
No problem at all. Any further question? I also have another, at least. So it comes, I think, as more or less a byproduct of say Prognosis.
Yeah.
But to me, it felt say a possible opportunity. And you were saying just a moment ago, well, yeah, we have all this supposedly equivalent implementations of a protocol, and we take one as a trusted implementation, and then we compare the others to that one. But even if you say, well, don't trust any of the implementations, at least you get something that that can say whether those implementations are equivalent or not, right? And this does not seem like a small thing.
No, this is actually, so this was one of the things that we were not expecting somehow. We hadn't thought about it when we started doing the work. And then once we realized that actually, well, we have all these implementations, let's just compare them. We actually, one of the nice things is that it gave us insights about the design choices that some of the programmers made. And some of them were really a bit puzzling. So the thing that led to non-determinism in the Facebook implementation, it took a while. So Tiago joined the Slack of Quick developers. There's a Slack for Quick developers where there's, since it's a new protocol, people sort of talk about how to implement certain parts. And it took a lot of days for him to be able to explain to the developers what was going on, and for the developers to recognize that their design choice had sort of inadvertently given rise to some sort of non-determinism. And debugging that took days. I mean, this was like they knew a trace that would cause it. They knew how it would be caused. And even then, debugging it was not easy. And this sort of gave us a glimpse on how different things work. And are we still streaming to YouTube? I wanted to make a comment, but as long as the stream doesn't stay on. So we tried to learn the Microsoft implementation, and we weren't able to. And it was really puzzling, and we will be talking to them, I think, about it. But the protocol was implemented in such a convoluted way that we couldn't even get the tool to give us a little fragment. It was really striking that we couldn't. I mean, whereas with Facebook and Google, after a few hours, we could get outputs. With Microsoft's implementation, there was something there we couldn't get in. There was something really, really strange about the design choices they made in the way the thing was implemented. So it's sort of, it's fascinating. I should probably have said Company X. I now realize this. I have to get better at this. Company X's implementation was not even suitable to interact with the tool, which was a bit weird.
I see. So thanks again. Any further questions? Maybe also opening the possibility for people to ask questions in Portuguese. I think most of us, if not all, do speak Portuguese. So if that's, say, preventing someone from asking a question, do feel free.
If I can still answer in Portuguese.
So I guess not. But well, anyway.
It's been a great pleasure to be here. And many years ago, I attended in Natal, and I'm hoping that in the near future, I'm able to attend again somewhere in Brazil in a nice location and meet many of you in person. That would be really, really wonderful.
No, it was a pleasure for us having you. SBLP starts today and continues tomorrow. So hopefully we will be able to, further discuss this and other, things. So stay tuned.
I should say, if anyone wants to speak to me or to know more about this, feel free to reach out by email, and I'm happy to set up meetings to talk about this work. And Tiago is also very excited about this, and I'm sure he would be happy to talk with anyone who's interested in seeing a demo of the tool and how it works. So please do feel free to reach out in Portuguese or English or any language that I can sort of follow.
Dutch would work anyway. At least Dutch.
And a bit of Portuñol or Spanish.
Okay, so thanks again, Alexandra. It was great. Okay, thank you.
Thanks very much for the invitation. Thank you.
Thank you. Bye-bye. See you all. Hopefully you'll continue to the next sessions, okay? So bye-bye. See you soon.
See you soon.
Bye-bye. Cheers.